Yes, please.
Okay. Thank you, Fatime, for inviting me to give this talk and share my thoughts and perspectives on the world of AI. It's become very relevant in the news these days, and I just wanted to share some of the concepts, techniques, and applications that underlie AI. Kind of go a little bit under the hood and give you guys a perspective on what works and what doesn't. So um, the the agenda is that I'm gonna talk about the overview of AI, different types of AI that's out there, and then we're gonna dive into one specific domain called machine learning, which has been really a very, very successful application of AI in the last 20, 30 years. Talk about supervised learning, unsupervised learning, a bit under the hood, how these things work, what they're good at, what they're not good at. Talk about how you just evaluate performance, and then close with some, pitfalls and things to watch out for, and so maybe some thoughts on the future. Okay, so let's begin. So first of all, as many of you realize, AI has been around for a very long time. Only recently has it kind of captured the imagination of the media with the advent of ChatGPT, but the field of AI is very broad, and it goes back all the way to the 1950s with early systems playing games like tic-tac-toe or chess, early knowledge bases, and then moving on to in the 80s and 90s with the advent of the internet and Google search and e-commerce, Amazon, email, to machine learning, right? To a type of AI that we'll talk about, but that's kind of in the 90s and 2000s, and now moving into deep learning, which is the foundations of generative AI, of large language models, of ChatGPT. Deep learning is just another name for of an algorithm in machine learning. So, but all of these are types of AI, and let's go a little bit deeper into each of these and understand kind of what they're all about. So let's talk about the first type of AI, what are known as expert systems. And so what does that mean? So what that means is that human experts, domain experts, encode all of their knowledge into rules or heuristics, right? And the role of the human is to basically do it all. You take all of your intelligence, experience, knowledge, and you put it in code, and the machine just runs the code. It just executes the code. There's no learning involved. And for example, there's a great example of this that all of you have right now is a calculator. A calculator is an expert AI system, and it knows very well how to add, multiply, subtract, and divide, among other things. But it has that intelligence. It's an expert system, and humans have coded all the rules of addition and arithmetic into it, and it just does it, right? Or maybe one of the chess computers that were popular back in the 90s, even Deep Blue, if you remember that, back from the 90s, first chess computer that was famous, beating some of the chess champions. It was an expert system. It had all the rules of chess and board positions and piece values built into it to play chess, right? Or another example would be a weather simulation, weather forecasting using partial differential equations that that humans have come up with and have encoded into the AI, right? And so they're great for well-defined problems with fixed known sets of rules, what I call the truth, right? And they are not probabilistic by design, meaning they will always give you the same answer. When you ask a calculator, what is 2 plus 2, it'll always say 4. And you depend on that. If it didn't say, if it sometimes said 4.1, that would not be a very good calculator, right? So that's the thing about expert systems. They're very good for when you know all the rules. So they have their limitations, obviously, right? What if you don't have the experts, right? What if you don't have human experts? What if you don't know all the rules, right? So then you move into this area of machine learning, which is what I which has taken off with the internet and e-commerce. And these are systems that will learn the rules from the data, right? So a very popular technique, and we'll talk about this in a little more detail, is what's called supervised learning. But in this situation, what is the role of the human? The role of the human now is you provide data, right? You provide some learning algorithm, whether some algo. You provide things, useful features, or useful rules that might be interesting to solving the problem, and you provide the target, what you want to necessarily predict. And the role of the machine then is to discover the combination of rules that best predicts the target. So you can see, compared to expert systems, the human is offloaded a little bit from providing all the intelligence. The human is just is there to provide the data, the algorithm, the features, and the target. So what are some examples? Fraud detection in banks, right? In banks and credit cards. So a bunch of data. We don't really know what's fraud, what's not. We don't know the rules. They're constantly evolving, but we can identify, whether fraud has happened or not. So we have a lot of data telling us that this was a fraudulent transaction, this was not. And we want to build a system to predict that. Or we're doing web search. Tons of web pages, search, user types in a query, what website will get clicked, what website will not get clicked. So these search engines like Google try to predict which result is going to get the most clicks, and they put that at the top of the search result, right? Or maybe handwritten character recognition, right? So you go to a bank, you insert your check, it reads from your handwriting, everything. So that was designed using supervised learning, where we gave it a lot of data and said, this is a 0-9, this is an A to Z, figure it out, right? So again, these are great for when you suspect some truth may exist out there, but you don't know what it is, and it's maybe not very well defined, but you have lots of data. You have lots of data to maybe approximate that truth in some probabilistic fashion, right? So these things don't always give you the same answer and aren't always 100% correct, but that's often good enough to bring some real value and real difference. And that's what's going on in the internet all the time, right? All these probabilistic systems. So, then a subfield of machine learning is kind of where we are now, generative learning or generative AI, or what the media calls artificial intelligence. In this case, we go up a level and have the systems actually learn the data. Now we're not providing useful rules. We're not providing any targets. We're just providing, hey, here's a bunch of data. Here's a learning algorithm, like a network or something. And, and we ask the machine, see what you can find out, right? Do it all. Find the relationships in the data, find patterns in the data, see what you can come up with. We'll talk about that more later on in the talk. I'll give you an example. But so you can see the evolution from expert systems, humans doing everything, machine learning, humans doing some things, and now generative learning, humans doing less, right? Just providing data and the learning algorithm and the resources. So some examples, of course, autocomplete in text messaging apps. So you using WhatsApp or your text messaging app, you see the next word, right? That was just the machine figured that out by looking at hundreds of millions of conversations and patterns and determining how the language works. Or like ChatGPT is another one of these examples. ChatGPT kind of crosses the boundary between supervised and generative. I'll talk about that in a bit, but or image generation models like Stable Diffusion, where you just, it can paint new pictures that didn't exist before. And these are great for when it is impossible to learn the data, to label any data. How can we label what next word is going to come out? Or how can we label, a new painting? Or the target isn't obvious. Sometimes the next word you might want to say is going to be to make a joke, or the next couple of words you want to say is you want to be serious. So the target isn't obvious either, right? So they're very much harder problems, and they require a tremendous amount of data and computational resources. And intuitively, you can kind of imagine this, because I can train somebody very easily to recognize whether a picture has a cat or doesn't have a cat. Okay, that's supervised learning. But if I have to teach somebody to paint a cat from scratch, that is a much difficult problem, sometimes impossible problem, right? So that's why it requires much more resources to teach somebody to draw a cat or paint a cat or create a poem from nothing, right? So, and of course, they're also probabilistic by design. So people, some of you may have heard of LLMs that hallucinate. Yeah, they hallucinate because they're probabilistic. They don't understand the language, they just go with the flow, right? So, so that's kind of a broad spectrum of AI. And let's get into it, what exactly are the different, maybe into machine learning a little bit more to understand what's going on. Before we do that, right? Vadim, you ask me, you've talked about the different methods. All I hear in the media is Gen AI, Gen AI, Gen AI. Why spend time talking about all this other stuff? Well, don't take it from me. There's a very famous machine learning researcher called Andrew Ng, and he gave a talk on YouTube recently. There's a link here about where's the value in AI coming from, and today versus 3 years. And you can see that most of the value today, and probably in 3 years from now, is going to be based on supervised learning, right? The kinds of stuff like we talked about, fraud detection, e-commerce, internet search. That's still where the money is. Generative AI is going to happen, and it is happening, and it's going to be a big thing. I'm not downplaying it. I'm not poo-pooing it. I'm just giving you kind of flavor of where things are really, at in terms of value right now. So it's still important to understand how these things work, because they also have a lot of connections to generative AI and some of the way those things work. So I hope that is a little bit of motivation why I'm going to talk about supervised learning, unsupervised learning. There's also reinforcement learning. It's very important. I'm not going to touch that. There's lots of resources about that on the net. Okay, so with that, let's dive into supervised learning, and under the hood a little bit. Okay, so what's going on here, right? So as I mentioned, you're trying to predict something. You have data like fraudulent transactions or pictures of cats, and you have labels. Like, this was a fraudulent transaction or not. This was a cat or not. That's your Y, that's your label. And you want to build a system that can predict this Y from some new X. Right? So there are different types of models you might hear about, or algorithms you might hear about in the literature, like linear regression, holistic regression, decision trees, neural networks, LLM fine-tuning is even supervised learning. Lots of names. This is not an exhaustive list, but just in case you run into them in the literature, this is how they work. So there are two main areas of supervised learning. One is called classification, and one is called regression. So in classification, it's the job is to classify, label something, and can be like two class classification, like I'm showing here, or multi-class classification, right? Different types of classes. So for example, what I'm showing here is, okay, I've got my data, and my data are these XY coordinates of a point, and the label is green or blue, and this is how the data shakes out. And my job is to predict, given some new coordinates, what is the probability that that is going to be green, given the coordinates, green or blue, right? So that's classification. Regression is another type where the data and the prediction are both real values. So in this case, a toy example, suppose the x-axis is like a speed of a car, and the y-axis, the label is the braking distance, and you want to estimate, or you want to design an AI system that will predict or estimate braking distance versus speed. This capital F, this function that sort of approximates the data in the best possible fashion. I'm not going to get into best, but there are various ways to do that. And so that's kind of the two classes of problems. So given that setup, let's take a look at an in-depth example on how these things work, right? So here I pulled this toy example off the internet for classification using an algorithm called decision trees. And the way this works is all supervised learning problems. You start with some data. So here we have some data on whether the goal is to design an algorithm to predict whether we should play tennis or not, right? That's the problem. Should we play tennis, yes or no, given some environmental data? So we have things like outlook, temperature, humidity, and wind. And then somebody has labeled each of these instances as you should play tennis, you should not play tennis, depending on these conditions, right? So somebody has gone off and created these labels Y, given this data X, okay? And also we have chosen these for environmental factors. We think these are useful, right? We could have chosen a whole bunch of other ones. So that's where the human intelligence came in. Human intelligence came into the fact that we chose outlook, temperature, humidity, wind. We didn't choose, the housing prices in Santa Clara as a possible feature or attribute, right? We kind of said that's not very useful. Let's stick to something that might be useful. So that's where the human intelligence came in. Right? And so we got this data, and our job then is to build this tree classifier that will sort of look like this. It'll at the bottom it'll have yes, no. You can think of it as a big if then else statement. And our job is to create a fill in those gray dots, right? What are those decision criteria that will make the system perform well, right? So that's the setup. And let's see how this works. So before we get into that though, I have to pause and take a step back and say that supervised learning, unsupervised learning, whatever learning you're talking about, if it's data driven, right, the number one principle of machine learning, of all of machine learning, is what I call for the greater good. And this is one of my favorite movies from the 80s when I grew up, Star Trek 2, awesome flick. And a quote, that says logic clearly dictates that the needs of the many outweigh the needs of the few or the one, which means that given a big data set, this thing is going to try to make the fewest mistakes, right? And it's going to try to optimize for the greater good. It's going to make some mistakes. It's not going to make everybody happy, but it's going to try to make the most people happy. So that's the fundamental underlying principle of all of this. Okay? So with that in mind, let's see how this works, right? So here is our data set again. And we got to start with some, something, one of these columns, one of these features to start with. There is a principled way to determine which one. Trust me, I'm not going to get into this, but just believe me when I say it's outlook. So let's say we start with outlook, right, as our first decision point. If we start with outlook, we notice that, hey, what do those rows look like? Well, outlook is overcast, right? If outlook is overcast, then the answer is always yes. So that's a great leaf in our tree. If overcast, then say yes, and you'll be right 4 out of 4 times. You're perfect, right? No mistakes. Okay, that's great. What about if it's raining? Well, if it's raining, it's a little different situation, right? We don't have a clear answer. We have 3 yeses, right? These 3 yeses, these green ones, and 2 no's. So what does the principle of greater good mean? Well, it means that we're going to say no. We're going to say yes, right? We're going to say yes. We're going to be wrong 2 out of 5 times, but hey, for the greater good, we're going to say yes. Also, if we look at sunny, right? The other option for outlook, we have 5 cases. 3 of those are no, and 2 of those are yes. So again, we're going to go with the majority, right? The greater good, and say no for that situation. Say no. You're going to be wrong 2 out of 5 times, but that's the way it goes. And so you're correct 10 times. You're wrong 10 times, 4 times. So 10 out of 14, not too bad. but not awesome either, right? We could do better. Right? We can do better. So how do we do better? Well, we take a look at each of these no nodes, right, and see if we can go deeper and make it a little bit more refined, right? So if you continue this pattern, right, you can transform one of these nodes into looking at humidity. The other nodes you can look into wind, and you'll get a deeper, more complicated decision tree that is now correct 13 out of 14 times, only makes one mistake. So that's good, right? You're going, you're learning supposedly, right? You still have this one mistake though, right? You still have this one mistake here in humidity high. You say no, but there's that one yes that you didn't capture. So maybe we can do even better. And so you go, okay, let's do even better. Let's split that into a decision based on whether it's temperature is not cool or cool, and then you'll be perfect. 14 out of 14, you ace it, you're done, right? But you have to ask yourself, did we learn anything? Did we learn anything, or did we just memorize this table? Did we just memorize this table? What about the other 22 out of 36 cases, right? If you look at those, if you go back and look at that table, there are actually, three types of outlook, I think three types of temperature, two humidity, and two wind. That's a total of 36 possibilities, 36 possible rows, and we only had 14. And here's our algo. What about the other 22? So, that's the tension here, right? How far do we learn, or are we just memorizing and without being able to generalize to new conditions, right? So how do we tell you're learning? So what we do often in this field is we draw this chart, this graph. On the y-axis we have error or mistakes, like how many times we're making mistakes, and on the y-axis we have this we call model complexity. So in our picture, you can imagine the model complexity as the bigger and deeper the tree, the more complex the model. And so, as we make the model more complex, adding more layers to the tree, for example, are the error or the mistakes we make on our data, our training data, go down. But if we then look and see as we make the model more complex, if we have some other data, maybe those other 22 out of 36 cases, and what we call validation data, we'll see that mistakes on that data that we did not feed to the algorithm, the mistakes at some point will go down. Yeah, we're learning. And then what's going to happen is at some point, we're going to find that we're memorizing the data. We're not really learning anything. And so I teach math part-time at De Anza, and this is kind of akin to, the blue line is akin to you doing your homework, right? You're doing millions of problems. And the question is, are you memorizing the problems? Like, are you memorizing every single derivative? Are you memorizing every single integral? Or have you learned how to differentiate and how to integrate that when you actually get an exam, like the red line is like an exam. The red line you can think of as midterms or exams, and you're going to make more mistakes in them. So that's exactly what's going on with these systems. Are they memorizing or are they learning? And you don't really know that until you find out, ask them. So very analogous to how people learn as well, right? So, and there are technical terms for these. There's underfitting, like you could fit the data more because your validation set error is decreasing still. But then you get in this region, it's called overfitting because you're really just memorizing. So overfitting is another word for memorizing the data without learning anything. And that term is very something to watch out for in machine learning. Okay, so that's how kind of supervised learning works. What about, like, how do you evaluate them, in the field? So let's talk about that briefly, just giving you some insight into that. So I'm going to motivate this with this example of a credit card fraud detector. So you get hired you're an AI, ML guy or lady in a bank, and your job is to build a credit card fraud detected, right? And you do some data analysis and you find that the rate of credit card fraud is maybe 1 in every 100,000 transactions. Very low, right? We have billions of transactions happening on the internet. And, so the rate is very, very low. I did some research and it looks like it's about 1,000%. Okay, so you think, okay, well, a metric of performance could be accuracy, as defined by the number of correct predictions divided by a number of total predictions. Right? That's what accuracy means. So you get this brilliant idea. Okay, I'm going to build a super accurate but quite useless AI system that just says no. Right? For example, you have transaction data coming in, and you build your system with like one line. Just say no. All good. It'll be 99.999% accurate, but completely useless, and you'll be fine. So that can't work, right? So this is not a very good measure. Accuracy isn't always a very good measure of whether this AI is working or not. So what are some of the other ways that we do this? And the way we do this is what's called a confusion matrix for classifiers, right? It has a 2x2 matrix, and it has these 4 cells. So imagine we're trying to predict whether an image is of a hot dog, a food that you want to eat. And so there are 4 different cases. So in the bottom right, we actually have a hot dog you want to eat, and the system labels it as hot dog. So that's a true positive, right? In the upper left, we have a pizza and the system says not hot dog. So that's good. That's a true negative. Okay, that's where you want to be, right? The true negatives, true positives. On the upper right, the system has said that's a hot dog, and it's not, right? It's not a hot dog. So we have made a false positive, right? We've said it's a hot dog, but it's not. So that's a false positive on the upper right. And on the lower left, it is a hot dog, right? But we said it isn't, right? The system said not hot dog, so that's a false negative, right? So this is the confusion matrix. And what the 2 things that come out of this, the 2 metrics that come out of this, one is called precision, right? Which is the ratio of true positives to true positives plus false positives. And this metric is important in e-commerce recommendations, right? Why? Because if you're going to, let's say, send somebody an email about something they might want to buy, or even more intrusive, you send them a notification on their app like, hey, Vadim, we think you should really look at this tennis racket. It's awesome. You better, have something good to say. If you're going to annoy me, then it better be good, right? It better be a true positive, right? I don't want to, don't spam me with just everything that you might think is good. Only tell me something when you really have something to say, right? That's why precision is very important in like recommendations, right? The other metric that we can think about is what's called recall, which is defined as true positives over true positives plus false negatives. And this is a measure of like, how many things did you leave undetected? Right? How many things did you leave on the table? And this is important in fraud, right? In fraud applications. Why? Because it's okay to maybe tell somebody, hey, do you think this might be fraud? Do you think this might be fraud? Do you want to confirm yes or no? And the customer will say, oh yeah, it's fine. Thank you for telling me it's not fraud, versus not telling them, right? Having a false negative and it being actually, actual fraud, and then them losing thousands of dollars, right? So different metrics have different applications, and more important in different applications, right? So, in the fraud example before, I think recall would be something that is very important. How many things that you have to follow. So just because something's very accurate doesn't mean it is what you want. And again, here accuracy is, again, in this case, the blue divided by the whole matrix, right? And not the thing you want. So just a little bit of just food for thought. If you think about these systems, you want to ask maybe what's the precision, what's the recall. Now you have a little bit more insight into how they're graded, right? Okay, so let's move on and talk a little bit about unsupervised learning. So we talked about supervised learning. you got give you some perspectives on that. Let's talk about unsupervised. What's going on there? Unsupervised learning, again, I mentioned this at the beginning, is, hey, here's some data X. Here's some data X. Machine learn the relationships and the patterns in X. Why? Well, because we want to use that learning and the learning of those patterns to generate new data, right? So unsupervised learning is very related to generative learning, and it's like LLMs and to stable diffusion, because you want to understand the patterns in the data so you can generate completely new data that didn't exist, right? Completely new pictures, completely new poems, whatever that is, right? And again, I throw out some names here just in case you want to cross them. It's not important that you memorize them, but embeddings, latent topic models, diffusion models. The part of LLMs that is called pre-training is also unsupervised learning. So anyway, just some names. So let's motivate this with an example problem, right? How do we do this? So suppose this is the setup. Suppose you manage a website selling concert tickets, like StubHub. I know StubHub does a lot of things, but suppose you're a manager of a website selling concert tickets, and what you'd like to do is recommend upcoming concerts that your customers might be interested in, right? Someone goes to your site and you want to recommend potential new concerts for them to attend, because that's how you make money, right? So you have on hand millions of records of past purchase data, including customers' personal data, concert data. You have, let's say, 100 attributes. Here, I made this up. Like you have a customer ID, you have name, you have address, you have phone, you have their gender, age, event, metadata, etc. And so you have hundreds, let's say 100 of these attributes or features, and you're thinking to yourself, great. I mean, the more the better, right? Maybe I should add 200 attributes. I have 300 attributes. Like just throw as much data as I can into this, and let's see what happens. Well, there's a problem with that, and it's what's known as the curse of dimensionality in the field, and it's the curse of high dimensionality. It's not the curse of low dimensionality. And it's what it means is that if you add more and more dimensions, you need exponentially more and more data. So how does that work? So suppose you only have one dimensional data. Suppose you have one attribute, like the customer's age. So in a 1D space, right, in a one-dimensional line, maybe you look at it and you say, well, this blue dot is kind of like this purple dot. They're close together, so maybe they're similar. And the orange dot is like the red dots, like the green dot. They're close together. So you can kind of see visually that maybe these three are together, maybe these two are together. Okay, that's in one dimension. Suppose you add another attribute, you go to 2 dimensions, and now the data look like this. That same data now looks much different. Now it's not clear. Is it the green, the blue, and the purple that are closer, or is it the blue and the orange that are closer? And then maybe the purple is close to the green. Now things look much less clear and more confusing, and things get worse if you go to 3 dimensions. Now you have no idea who's similar to whom or what the patterns are, and you would need to understand the patterns in, let's say, 3D, exponentially more data. You would need 2 to the third more data. And now, if you think about, let's say, 50 dimensions or 100 dimensions, you would need something on the order of 2 to the 100th data points, something that is on the order of the number of atoms in your body, right? So it's like trillions of data points, which you don't have, right? So what do, right? You want to use much data, you want to use much information, but you don't have enough data. You have this question of dimensionality. So what do? What's the technique that people do? And the technique that is standard is called embeddings, right? If you read about or launch videos of LLMs or whatever, of any kind of large language model, ChatGPT, embeddings, you hear all the time. But embeddings fundamentally are a way where you take high dimensional data, like our 100 dimensions in this concert data set, and we reduce them to a lower dimensional space. And it doesn't have to be anything fancy. It could be, for example, this. I'm just going to reduce it from 100 dimensions to just two: age of the music band and age of the customer, right? I made this up, but that's an embedding. We've taken that information and we've embedded into a lower dimensional space. Now we have lost some information, right? We have lost some information, but maybe we have gained something in the ability to discern patterns, right? It's kind of the trade-off. So, and embeddings are at the core of all LLMs, right? They all start with embeddings, right? Of the language. So, so for example, let's say you did that and you plot the data and it looks like this. Oh, okay, so now maybe you can see some clusters in the data coming out that maybe you can make sense of, right? So with that in mind, let's see if we can actually generate some recommendations for a new user, right? We've got this data set, we've done some embeddings, we understand the data patterns. Let's see if we can use them to generate some new recommendations. How do we do that? Well, simple. New customer comes in. Here's a new customer, right? Someone you've never seen before. He's brand new to your site. You know some things about him, like his age, right? His age. So, okay, great. So that's where he falls. So maybe there's some distribution, some over those decades of bands, and you kind of draw that. And, maybe there's some top and bottom intervals. And you say, okay, well, this user kind of falls here, so maybe we should recommend 80s and 90s bands in concert. So now you've generated a renewed data point, a new recommendation for a new user X prime that you didn't exist before, and you did that by understanding the patterns and relationships in the data using embeddings, right? So that's kind of how those things work. Okay, so those are just an overview of the techniques and what's under the hood. And last thing I want to talk about are kind of this pitfalls in some of these things, and it's not and thoughts in the future. So where do things go wrong? Where do things go wrong? So the things always go on with data, right? This is the number one thing that always is at the root of all problems, right, in data science, right? And the adage "garbage in, garbage out" really holds, right? So that's where things go. Let me give you some examples, right? And it's because if you think of data-driven AI systems like LLMs or Stable Diffusion or whatever, they're all data-driven systems are designed to find and exploit, emphasis on exploit, similarities, patterns, and correlations, right? They will exploit things that you may not even know are there. Some random spurious correlations that you don't even realize are there in the data, but the machine will find them and it'll do completely bizarre and wacky things. Let me give you an example of this. So suppose we're trying to design an image recognition system, and we really wanted to know what a horse, like detect pictures of horses, right? This is a paper source below called Clever Hunts Predictions in Nature in 2019. So the objective was to build an image recognizer for a horse. So, okay, so you build one and you give it this picture and it predicts horse. Like, awesome, it's working great. Then you give it a picture of a car and it says no horse. You're like, okay, so far so good. So you think you're doing great, but then you give it this picture and all of a sudden it tells you system outputs no horse. Like, what? That horse looks just like the first horse. What's going on? And then you give it this picture and of the same car, and it tells you that there's a horse. So what's going on? Well, what's going on is that what the system actually learned is nothing about a horse, in that it keyed off of this text overlay that was in all the horses. Like this text overlay in the lower left-hand corner is what the thing was in all the horse pictures that you gave it to learn from. So it just figured out that must be the horse. And it doesn't know what a horse is, right? These things are like toddlers with an infinite memory, close to infinite memory and processing power, and they don't really know anything. They just know what you tell them. So if you give them a million pictures of horses with this thing, they'll probably think that's the horse right there. So again, data. Be really careful. Another example is, well, maybe sometimes data isn't what you need. I mean, more data isn't going to solve the problem. This is from a paper, recent paper, where the authors tried to motivate LLMs, large language models like ChatGPT, as calculators. And here's a table showing, the performance of, of ChatGPT, as well as really tuned models called MathGLM on just arithmetic, right? On just pure arithmetic. And you can see that, ChatGPT, first of all, is horrible, right? Like 1%, 3% accuracy on 8-digit arithmetic. Their model is much better, 65%, 67%, but still it's like 2 out of 3. So throwing more data at this isn't gonna maybe get you to like 95%, 99% accuracy, but would you fly an airplane that was designed with calculators with 99% accuracy? I wouldn't. So sometimes data, just throwing more data at the problem isn't the answer, right? And so, I want to just conclude with these thoughts that, and this is a famous quote by statistician George Box in 100 years ago. He said all models are wrong, but some are useful, right? And you have to understand what they're useful for, right? What they can do, what they cannot do. Do not just blindly take their output and run with it, right? So as you guys are thinking about, your future careers, what to do in the landscape of AI. I know you guys saw the Super Bowl, and there was an ad by Microsoft. The Copilot looked like it could do everything for you. Just sit back and Copilot will write the code, will do everything, right? Yes and no, right? Yes and no. I think the game is changing very rapidly. I would advise everybody to just stay curious and understand, how the sausage is made. What is behind the models? What were they trained on? Understand the capabilities and limitations, and think how can you make the AI work for you? Don't just consume it blindly. Get curious, and stay up to speed. I think the software development field is going to evolve. It's not going to stay the same, but it's not dead, right? There still are going to be software developers, but the nature of programming will change. Maybe we can talk about that more in the Q&A. But I hope this was a little bit informative glimpse into what these things do, how they behave, and what to think about. And yeah, thank you. Thanks for your time. I'll open it up to questions in the last 15 minutes.
Thank you, Vadim. I appreciate that. It was very informative. Thank you for sharing all of this information with us. We have a question in the chat. How would you treat the outliers? Is there any specific solutions? Like, do you eliminate them in general?
Yeah, so outliers, are a problem in general. I think the first step is to be able to detect them, and there are ways and models that one can use to detect them. But in general, you don't want to just throw away data unless you understand that it is an outlier. Like, are you sure this was their mistake collecting, right? Because it might not be an outlier. It might be actually some foreshadowing of the environment changing. So don't just indiscriminately drop outliers because they make your model fit bad.
Thank you very much. So in general, what's your advice for students who are interested in following your path, going into data science and data analytics in general?
Yeah. So couple of thoughts, right? So I think there's some fundamentals that are good to understand. So it is good to understand statistics, Right? Statistics is a fundamental discipline that has wide applications, and some of the foundations um, are key to understand. Even you build a model and then you have to um, test it in the real world. So after we build models, we test them. We run what are called A/B tests. Um, treat control versus treatment. We measure statistical significance. So understanding that is also good, and understanding data, how how regression models work is key. I think understanding um, computer science. So I mentioned this earlier a little bit. I think studying computer science helps people understand how to break problems down into subcomponents and logically reason through. I think that the act of coding itself will maybe evolve. Maybe syntax of languages will become less and less important as things like Copilot are there. And I think maybe a lot of people speculate. From what I've heard is that the new programming language will be just be English. You'll just type English and out will come code. But that doesn't mean that the code will be great or free of problems or will actually be efficient, and the architecture component will be missing. So studying computer science, understanding architectures um, will be important, right? And then like I think those two things I would advise. And then as you get more familiar with statistics, coding, of course, um, like math, linear algebra is important. As if you depends which career you want to take. If you want to go into AI research, right, develop new algorithms that would say double down on linear algebra, vector calculus, all those things are going to be important. Matrix operations, or you want to go into more kind of coding, which is understanding how these things work and how to use them best. I'll stop there.
Thank you very much. We have a question in the chat. Would you categorize supervised learning as AI?
Sure. I would categorize a calculator as AI. I mean, there's AI is a very broad domain. I think it's only now people think of AI as ChatGPT. I wouldn't. People are trying to get to generalized AI. I mean, maybe what you're thinking about is when you ask that question is, generalized AI, kind of what equivalent to what humans can do, right? So we're not there yet. We're not there yet. ChatGPT has problems with logic and reasoning. It doesn't really understand some basic logical foundations. So we're not quite there yet. But supervised learning is AI. Right? It is broadly in the AI domain.
Thank you. And what's the impact of AI on the job market?
Yeah, so that's a good question. I think the job market will have to evolve, right? I think some basic, some repetitive tasks that can now be automated will probably will go away sooner or later, right? I think we'll transition into more creative roles where you have an idea and you want to execute it. It'll make the AI will make that execution easier. I think some of the repetitive tasks of maybe, let's say, if I think of something like QA, let's say like there are jobs right now like QA jobs where you're given a functional spec of a system and you're asked to write the QA code, the driver code that will test all of the functionality written in the functional spec, right? There are people who do this. They read the spec, they write the QA code, and they run the QA code. I think that is probably at risk to AI. I think the AI will be able to read the functional spec, write the QA code to do that. But at the same time, if I think about AI is not going to invent the next system. For example, analogy I like to paint is, imagine you're in 100,000 years ago, and all there are sailboats, right? They're just the ships with sails. So AI is very good at telling you maybe a new sale configuration, maybe like 4 sales or 5 sales, maybe like perpendicular sales or whatever sales. But the AI isn't going to invent the engine. It's not going to look at a bunch of sailboats and say, you know what we can do? We need to forget all that and build a gas-powered, combustion engine. Right? It's not going to do that. So I think it's going to be up to us to be those that to have that creativity and that intelligence to envision those kind of transformational systems that the AI is not ready to do yet.
Thank you. Question in the chat. Do you think Tesla's AI robots can become a problem?
By problem, you mean, I'm not sure what you mean by problem, like in terms of like Terminator problem kind of problem. I don't know. I think, again, there is an active, so one of the active fields in AI, right? So now these AI systems hit the scene. So what are the open problems in AI that people are working on? So one of them is, of course, safety, right? Safety, fairness, bias. There are, governments are setting up committees to ensure that these things don't do any harm, that they can perform logical reasoning, and that they limit misinformation and hallucination. So this is a very active domain in AI, is how to make these things safe and fair and prevent hallucination. So I think it's something we need to keep a close eye on. But no, I don't think that, like next year we're going to have Terminator type scenarios, if that's what you mean by problem. I think, now you have like Roombas, people have Roombas doing their vacuuming. I think maybe we'll have some form of better, more intelligent Roombas and things like that in the next few years.
Thank you for wrapping that up. I think the student, Ethan, had the same type of question. They're mainly worried about the safety or if it's going to be problematic in the future. And one last question is, can a generative model be used to create inputs for supervised model?
Yes, so both ways. Actually, that can work both ways. A supervised model can be used to give feedback to a generative model, and a generative model can also be used to create labels for supervised model, right? So this is before generative models were around. There's something called semi-supervised learning, which I didn't talk about, is where you would kind of use one model to generate some labels for another model with the knowledge that there was going to be some noise there, but the fact that you were going to generate a lot of labeled data outweighed the noise. So that's been around, right? In the form of semi-supervised learning.
Thank you very much. And do you have any one last advice for our students in college?
Yeah, just one last advice, stay curious. I think, hey, this is going to be biased advice. This is going to be biased advice because I'm a math teacher. So study math. I think if you look at all the stuff that is out there today, the math behind it is hundreds of years old. Like matrix multiplication, right? Differential vector calculus, differential equations. The concept of neural networks, like, was invented, I think, in the 50s and 60s. The first perceptron, I forget the exact date, was over 50 years ago. The reason it took time to come to fruition is because of processing power. But the math is hundreds of years old, decades old, right? The math is constant. The math is constant, and it's just finding new applications in AI. So if I had to double down on studying something, I would study math.
Thank you very much. We appreciate your time. Students, I'm going to take one last question. If you have any question, please unmute yourself or post your question in the chat.